In this talk, we'll see three geometric problems that bothered the Greeks, like a square in a circle. It bothered them because they were able to solve harder problems and similar problems, and yet these three problems, they didn't make it, even though they tried very hard. And since the Greeks didn't make it, other mathematicians in the following centuries tried as well and also didn't make it. Until somewhere in the 19th century, it was proven impossible. It was proven impossible using modern algebraic tools. So most of the lecture will be on these algebraic tools, which are needed to show the impossibility of these constructions. And finally, we'll use those tools to do some geometry. So what do I mean by possible and impossible? So this definition by the Greeks, of course. So let's say you should be able to do these constructions using only a basic ruler and compass. So a ruler is just a ruler, no marks on it. The only thing you can do with the ruler is just draw lines between two given points. With the compass, the only thing you can do with the compass is put the compass two ends of the compass on two given points and sort of take the distance between those points and then draw a circle around some other point, possibly a different point. So in this case, the construction I want to do is, let's say I want to find the middle point between the midpoint between the two given points. So I use the ruler and make this section, and then I use the compass and make this circle. I put the compass on the second point and make another circle. Now I have intersection points, which were born out of these constructions. Again, I use the ruler to draw a section between these two intersection points. And Euclid showed that the intersection between these two sections happens to be exactly what I wanted, the midpoint between the two given points. So this is a construction that is possible. There are many constructions that are also possible, like this one. So you can divide any segment into equal sub-segments. You can construct the half of a given angle. You can find a square which is the same area as the given polygon of several sides. You can do all sorts of arithmetic. You can divide, multiply, take square roots even. But you cannot do these three constructions. Now it's proven impossible. So the most famous problem that you cannot do is square in the circle. So given a circle, you want to find construct a square which has the same area of this circle. So if the circle happened to be of radius 1, then the square would have to be of the side pi, square root of pi. Other problems that we'll also see are impossible. Is given a cube, doubling the cube. So if you have a cube, you want to construct a cube of double volume. That's impossible using just a ruler and compass. And you cannot trisect given any given angle. So you can trisect, meaning you want to find an angle which is the third of a given angle. So you can do it for some angles. You can trisect 90 degrees because it's easy to construct 30 degrees. But you cannot do it to any angle that you want. For example, you cannot trisect 60 degrees. You cannot find 20 degrees. Okay, so I'll start with the spoiler of the whole proof. So if you forget anything, which is probably going to happen in a week or so, so at least remember this. So suppose that you were able to take a circle and create a square of the same area. You're using just a ruler and compass. So you said that when you use a ruler and compass, you just collect more and more points. You make lines and circles and collect intersections points, and then use those to construct more lines and circles. But on the way you construct a sequence of points, and each point on the way is an intersection of lines and circles that you constructed previously. And it happens that the coordinates of these intersection points, if you go ahead and try to find out what they are, you see that you have to solve equations of degree 1, 2, or 4. So if you want to find the intersection between, say, a line and a circle, you just have to solve an equation which happens to have a degree 1, 2, or 4. Depends on the particular case. And the equations and the coefficients, of these equations are dependent on points that you constructed before. So you construct some points before using these intersections. You solved some equations of degrees 1, 2, and 4, and now you use those historic points to create new points, which again require solving new equations of degrees 1, 2, and 4. And if you collect all these equations together, it's equivalent to solving into one big equation of degree which is a power of 2. So any point along the way, any point that you can construct with a ruler and a compass, you can think of it as a solution to some equation which has a degree of the power of 2. And okay, but if you want to double the cube, it so happens that you get a coordinate which happens to be a solution to a degree 3 polynomial. We just declare that you can only create points that are solutions to equations of degree power of 2, and 3 is not a power of 2. So with a ruler and compass, you cannot double the cube. Similarly, if you want to trisect 60 degrees, you get 20 degrees. And if you have a 20-degree angle, you can find a solution. You can also construct a solution to a degree 3 polynomial, and again, it's not a power of 2. Squaring the circle is even more difficult because we saw earlier that you get a coordinate which has a square root of pi, and from square root of pi you can construct pi, and pi is not a solution to any polynomial. It's a transcendental number. Transcendental numbers are not a solution to any algebraic polynomial. Okay, so this is the plan of the proof, and most of the proof is going to use algebra. So just so we're on the same line, most of you know this, but I'll just repeat. So we're going to work with fields. You can think of fields, for those of you who don't know fields, let's just think of fields as a collection of numbers. They don't have to be numbers. In general, it's abstract algebra, so they could be fields of permutations and symmetries and stuff like that. But for our purpose, we're just going to use fields of numbers. So just think of them as a collection of numbers. But this collection of numbers comes with two operations, addition and multiplications. And these operations behave like you expect in the real numbers. So if you add, they are commutative, so a plus b is b plus a, the same for multiplication. They're associative. You have an identity element for addition, which is 0. You can add it to anything and get the same thing back. And there is also identity one, usually called 1 for multiplication. Addition is invertible, so you have a minus a for every a. Multiplication is also invertible except for 0, so you have a reciprocal for any value. For our purpose, the most important property of fields is they have to be closed. Meaning that if you have to take any two elements in your field and you add them or multiply them, the result is also in the field. So if a and b are in the field, the sum and the product must also be in the field. So if you take it, for example, the real numbers are obviously closed for addition and multiplication. So the sum and product of any two real numbers is also real. But as an example of a collection that is not closed, let's take the collection of all integers. It's also close to addition and multiplication. But if you take this collection and just add pi to it, so your collection is all the integers and pi. Okay, that is not closed for addition because it doesn't contain 1 plus pi. Okay, so that's an example of something that is not a field. The integers, by the way, are also not by themselves are also not a field because they don't have inverse, multiplicative inverse for most numbers. So 2 is an integer, but a half is not an integer. So the integers are not a field. So examples of fields, we mentioned the real numbers are fields. Complex numbers are also fields. We are most interested in the rational numbers. Rational numbers are fractions, where the numerator and denominator are integers, like 2/3 is a rational number, it's in Q. But pi divided by 3 is not a rational number because pi is not an integer. So the Q, the rationals are all the fractions over integers, like 2/3. And it is a field. You can check and see that it conforms with all these rules that we just gave. I said earlier that Z is the collection of integers, so Z is not a field because it doesn't have an inverse for all numbers. There is a version of Z of the integers, which is integers modulo some prime number, which happens to be a field. If you check, you find out that if you just work with the integers modulo some prime number, all the rules apply. But we don't really care about that. We just care about the rationals in this talk. Okay, so you probably know Pythagoras because of his theorem. He was actually he was at the head of a cult in southern Italy, which had many mathematicians in it. Beyond just the theorem that you know about triangles, he had other theorems as well. They were semi-religious and they had all these tenets. So one of the tenets was that everything is a number. Everything in nature, there's a number behind everything. And the relations between numbers are the fabric of the universe, as it says here. So relations are important, and Pythagoras is credited with discovering that the harmony of the laut is dependent on the ratios of the strings. So the 2/3 and the half would be harmonious, but if you take a seventh, it won't be, or something on that line. But anyway, ratios are important. Ratios are part of nature. And they have this other tenet that you should never do anything with Fava beans. That's full. And you see there, there's something against harming Fava beans. You shouldn't sit on them, you shouldn't harm them. And there's a legend that Pythagoras had to escape from his pursuers, but he wouldn't get into a Fava field, and therefore he died. But I'm not sure it's true, but that's what they say. Anyway, we were more interested in the tenets related to numbers. So one of his disciples, Hippasus, discovered that the square root of 2 is not rational. So there is no fraction of integers, like 2/3, which equals, which if you square it, you get the value 2. And so Pythagoras would express the same property in geometry. So it would look at the ratio of the segments, or looking at actually what they prove is that there is no common divisor between the diagonal of the square and the side of the square. But that's exactly equivalent to this statement. So anyway, there is the thing that Hippasus discovered is that this particular equation doesn't have any solution in Q, which for Pythagoras means that it doesn't have any solution at all. This is the proof, by the way, of Hippasus. I'm not going to go over it, but I can sometime. You're welcome to take a look at the video once it's done. It's a very elegant proof. I recommend every person of culture to know this proof, so you can take a look later. Okay, but what happened? What troubled Pythagoras is that this square root of 2 doesn't exist. There is no such thing in nature which solves this equation. And the Greek, not only Pythagoras, but the whole worldview of the Greek was that mathematics is part of nature, and mathematicians are just discoverers. They go and search for mathematical truths that exist independently. Just like if you want to discover the circumference of the Earth, you have to go and find out. So the same thing is in mathematics. So these numbers actually exist somewhere in nature, and you just have to go and discover them. And the fact that square root of 2 doesn't exist is troubling for this particular viewpoint. The modern view is different, and that is we don't really care about nature. We do what we like. Mathematics is a human activity. We just, if we don't find the square root of 2, we just declare it. We don't have to worry if it exists in nature or not. That's just the business of humans. There's 2 quotations here that from Kirchner and Russell about this point. So we are troubled from the fact that we don't find a square root of 2 in a collection of known numbers, which is, let's say, the rationals. So we just invent a number out of the blue. We call the number square root of 2, and we declare that it solves the equation that we're worried about. We're worried about x squared equals 2, so we just declare that this is a solution to this particular equation. And if you think of it, it's not more invented out of the blue than 5. So somebody wants to solve the equation x minus 1 equals 4. So you have to invent the number 5 for that. And 5 is a figment of imagination, just as like a square root of 2 is. Okay, so we had this equation, x squared equals 2, and it didn't have a solution, and we declared, we invented a new number, we call it square root of 2, which is a solution to this equation. And it's not in Q, so let's add it to Q. Let's take all the rational numbers and insert a new member to this collection, this new number that we just invented, and try to make a new field out of it. So if you just take the rationals and add square root of 2, it's not going to be a field, because it's not close to addition. If you take, let's say, 5 and if you take 5 and square root of 2, the collection must also include the field, must also include the product of these numbers. So 5 times square root of 2 must also be a member of this field. So we do it. So we also add 5 times the square root of 2 to our field. So in general, we're looking for the smallest field that contains all the rational numbers Q and also contains the square root of 2. Okay, so the real numbers is too much. We don't want all the real numbers, which also include square root of 2, obviously. We just want the rationals plus the minimum possible of additions that will also include the square root of 2. So this minimal amount of additions must contain every rational number multiplied by square root of 2. For this reason, it must also include the addition, right? So it has to be close to addition. So in general, it must include all the values of the form a plus b times square root of 2 for any rational numbers a and b. And it turns out that this is enough. So if you take all the numbers of the form a plus b times square root of 2, you get something which is close to addition and multiplication. So any value of this form, any two values of this form, if you add and multiply them, you get another value of this form. So this is the minimal extension of the field of rationals that contains the square root of 2. In this particular form, a plus b times square root of 2, it's what we call the linear combination of 1 and square root of 2. So you have this basis of value, 1 and square root of 2, and you combine them using the a and b coefficients taken from Q. So this is what we call a linear combination, but we'll see that later also. By the way, this is called, you can call it, this is a field extension, Q extended with the square root of 2. It's sometimes called the Q adjoined square root of 2 for short. Okay, so this form may look familiar, a plus b square root of 2. It's exactly the form of the complex numbers we take in I, and it's exactly the same story. We had an equation, x squared plus 1. We want to find a solution in R. R doesn't have a solution to this equation. So just declare a number, or invent a number out of the blue. We call it I. Declare that I is a solution to this equation. And then we try to extend R, the real numbers, with this new number I and see what happens. And again, if you want this extension to be closed to addition and multiplication, we have to have all the values of the form a plus bi, where a and b are now part of the real numbers. And what we get is obviously the complex numbers. Okay, so this, once we take this extension, R extended with I, minus I is also part of this extension because it has to be close to addition. So in fact, this extension, R extended, R adjoined I, has all the roots of this equation, both I and minus I. And kind of a fun fact is that the I and minus I are completely isomorphic. There's no difference between them. Because Pythagoras would say that that these two numbers exist somewhere in nature. There's some two numbers in nature that the square plus 1 equals 0, and we just give them a name. We give one of them the name I, and another we give the name minus I. We could have given them any name we wanted. The name's not important. What's important is that these two numbers that exist in nature are roots to this equation. But from our point, we don't really believe that. We think that we don't really care about nature. We just care about these definitions. We just define two numbers. Actually, the only thing that exists is these names, the I and minus I. And the property that we wanted, that the square equals 1. So they're completely interchangeable. There's this claim here that you cannot express any property of I and minus I as a polynomial, which will be, any property that is expressed as a polynomial over I will also hold for minus I when you change the names. Just again, I mentioned polynomials, so let's see what define polynomials for those of you who don't know, forgot. So polynomial over x is a function that has this particular form. It's a sum of terms, where each term is a power of x, of this variable of the function, multiplied by some coefficient. And the coefficient comes from some collection of valid coefficients. In our case, if you have a field, and the field contains both x and all the coefficients of this polynomial, then because of closure, it will turn out that p of x is also part of the field, because we just add and multiply. To compute a polynomial is just adding and multiplying, and adding and multiplying is a closed operation for fields. So if x and the coefficients are there, the result of the polynomial computation will also be there. There's this definition of a reducible polynomial. So some polynomials, like the one shown here, can be decomposed or reduced or split, several terms for this, into a product of lower degree polynomials. In this case, the polynomial is degree 2. It's 9x squared minus 4. We can break it up into a product of two polynomials of each of degree 1. Not all polynomials can be broken up in this way. So, for example, x squared plus 1 can be broken into lower degree polynomials in R, if you only allow coefficients in R. But if you allow your coefficients to come from R adjoint I, then you can break it up. Here you see, here we were able to break up the polynomial into a product of two terms because we allow ourselves to take coefficients from R adjoint I. So the coefficients, the question if your polynomial is reducible or not depends on what coefficients you allow yourself to use in the reduction. It's not always easy to know if it's reducible or not. There's some heuristics. The Eisenstein heuristic is used to know if to determine if a polynomial is reducible in Q. Don't really care. Let's see some more examples. So we saw this example. So this is a polynomial. It is reducible in Q, meaning that if you allow only coefficients in Q, you're still able to break it up. And it also has two roots in Q, 2/3 and minus 2/3. But it's not always the case. You can be reducible and not have roots. For example, this polynomial can be broken up as seen here. Its coefficients are all in Q. Also, when you break it up, they're still all in Q. But it doesn't have any root in Q because its root are square root of 2 and square root of 3 are not in Q. And we already know about this equation. We know from Pythagoras that it's not reducible in Q, but because there's no roots of this equation in Q. But if you allow yourself to take your coefficients from Q adjoint square root of 2, then it becomes reducible, like shown here. Okay, so just a quick breath before we continue. So we saw so far that we defined what fields are. It's a collection of numbers for our case, like the rationals, which come with operations like addition and multiplication. And the important property is that they have to be closed to these operations. And they have this structure of properties. You can commutative, associative, and so on. If you have an equation and don't have a solution in a field, you can always extend the field by adding a new solution of any number to this field. But you just have to take care that you add enough numbers so that the field remains closed. So if you add A and B, you have to add A plus B also. And finally, we saw the example of Q extended adjoint I, which has this form of A plus BI, where A and B are taken from the rationals. Actually, that's it. Okay, so let's continue. So extension towers is just when you extend a field with more than just one member. So in this case, we have an equation which has actually 4 roots. None of its 4 roots are rational. Let's say I want to add all 4 roots to the field of rationals. So I basically I create a tower of extension tower. I add both I and square root of 2 to the rational fields. And it's written out like this. So this is Q adjoined I and the square root of 2. It happens that the order is not important. You can see that if you add first I and then square root of 2, you get exactly the same field that you get if you first add square root of 2 and then add I. In both cases, what you get is what you see here. It's a linear combination in this time of 4 elements. So it's a linear combination of 1, I, square root of 2, and square root of 2 times I. Again, where A, B, C, D are all taken from the rationals. Okay. There's a justification for this claim. I will not go over it. Okay, so you have an extension tower of we wanted to add I and square root of 2. We got a linear combination of 4 elements. But it's a very particular type of linear combination because these 4 elements, the 4 elements are 1 I, square root of 2, and square root of 2 times I, are what's called linearly independent. So none of these 4 elements can be created from the other 3 elements just by using linear combination of multiplying those elements by rational numbers in this case. So when this is the case, when the basis of your combination is a collection of numbers that are linearly independent of each other, then this is called a vector space. So in this case, Q adjoined I and square root of 2 is a vector space, 4-dimensional vector space over this basis of linearly independent numbers. And an alternative definition of linear independency is that if you take any linear combination of these 4 values and they happen to equal 0, this can only happen if all A, B, C, and D are equal to 0. So this is just an alternative definition of what it means to be linearly independent. Okay. Another example of a vector space, we saw this before, we have Q adjoined I, which is the rational when we extend it with I. We saw that this has the form A plus BI, where A and B are rationals. And this is a vector space over the basis I and I, because 1 and I are linearly independent. You cannot get I from 1 just by using rational numbers. So now we come for a new definition. So the dimension of a field extension, like Q adjoined I and square root of 2, is the size of the vector space of the basis which spans this linear of this field extension. So, for example, Q adjoined I square root of 2. If you take your coefficients from Q, you get a vector space of size 4. You need a vector space of size 4 to span this, as we saw. And similarly, if you want to just use the Q adjoined I, you have a vector space of 2 numbers of 2 elements, and therefore the dimension of the field extension Q adjoined I is 2. So the dimension is just the size of the vector space, of the basis that spans the vector space. And this size depends on the coefficients. So if you take the same extension field, it's Q adjoined I and square root of 2, the same extension field, it will have different dimension depending on where you take your coefficients from. So if you allow yourself only coefficients from Q, then you need 4 elements in your vector space. If you take the luxury of using square root of 2 in your coefficients, if A and B can come from Q adjoined square root of 2, you obviously don't need so many. You don't need all 4. You just need the A plus BI, because B can include square root of 2 inside it. So you cannot really ask what is the dimension of a field extension. You have to ask what is the dimension of a field extension given some field of coefficients. Okay. By the way, the same holds here. So if you use the coefficients from Q adjoined I, you also need 2 elements. It will still be a dimension 2. Let's see some examples again. So the extension field Q adjoined I and square root of 2. If you only use coefficients from I, we saw that you need a vector space of size of spanned by of size 4. So the dimension will be 4 because this is the form of all the values. It has 4 elements. If you allow yourself to use coefficients from Q adjoined square root of 2, you just have 2 elements in your vector space. So the dimension of this extension is 2. If the same holds if you use the coefficients from Q adjoined I, again, you have a vector space of just two elements. So the dimension of this extension is 2. And finally, we saw this, the Q adjoint I. If you're using coefficients from Q, you get this form A plus BI, and this is again a vector space of size 2. So the dimension of Q adjoint I over Q is 2. So we have these 4 examples. And it's an arithmetic fact that 4 equals 2 times 2. So I just plugged in the values here. So on the left, you see the values that's here on the top, which happens to equal 4. And I multiply 2 values that happen to equal 2, right? This is the third element, and this is the last element. And so this is just a fact. If you multiply these 2 dimensions, you get these 4 dimensions, this other dimension. And this is a general rule. So if you want to find out what is the dimension of a field extension B over coefficients from A, you can try to find an intermediate field between A and B. In this case, it's called F. And just find out the dimension of the field extension of F over A, using the field F over the coefficients in A. And secondly, try to find out the dimension of B using coefficients of F. And if you multiply these 2 numbers together, you get the dimension of the tower, which is the B using the coefficients from A. And this is an example, right? You see here on the left, A and B is Q, and Q adjoint I in square root of 2. And here I found an intermediate field Q adjoint I, and I can compute the 2 dimensions of the intermediate fields, multiply them together, and get the dimension of the final field. Okay. And this is called the tower law. So let's see some examples. So let's say I want to have the field of rationals, and I want to extend it to get 2 new values, R1 and R2. I can do it in 2 steps. First, I extend Q into Q adjoint R1. I have some dimension for this extension, the vector space. And second step, I take this Q R1 that I just created and I join R2 to it. And again, I have a dimension for this field extension. And it so happens, because of the tower rule, that the product of these 2 numbers will be the dimension of the whole thing. So if of Q adjoint R1 and R2. And we saw the example before, right? If you take the Q adjoint I in square root of 2, using only coefficients of Q, you get a vector space of size 4, which happens to be the product of the dimensions of size 2 here, of two extensions of size 2. The same, because this is a tower law, it was also for any number of extensions that you want to do. If you have a tower of 3 elements, you can do it again in step by step. So you start with Q, you add R1, find out the dimension, and then you take Q with R1 and just add R2, again find the dimension, and finally you take R1 adjoint R1 Q adjoint R1 and R2 and join R3 and compute the dimension and multiply the 3 dimensions, and you're guaranteed to get the degree of the vector space of the whole thing of Q adjoint R1, R2, and R3. And there is a proof for this, which is very tedious, and I will not go over it. You can take a look at the video if you have it. Okay, and final definition that we need, algebraic definition, is minimal polynomials. So consider this polynomial x to the 3rd degree minus 2. This is called the unique, minimal polynomial of the third root of 2 over Q, which means that there is no polynomial of lower degree than 3 of which the 3rd root of 2 is a root. So you cannot find any polynomial of degree 0, 1, or 2 that has the 3rd root of 2 as a root, with the important requirement that this non-existing polynomial must have rational coefficients. So you cannot, actually you can take it as an exercise to prove that there is no polynomial of degree less than 3 which has only rational coefficients, which this is a root, which the 3rd root of 2 is a root. You can prove it from the fact that all the 3 roots of this polynomial are irrational. Okay, so Okay, just to be formal, so minimal, again, minimal polynomial over some root. This root has to be a root of the polynomial, so third root of 2 has to be a root of our minimal polynomial. The minimal polynomial must be irreducible. You cannot break it up using just coefficients in Q. And there shouldn't be any smaller polynomial which has the same properties. So in this case, we don't have a smaller in the sense of the degree. So in this case, we don't have any polynomial of degree 2 or 1 or 0, which has this value as a root. Okay, so this is a minimal polynomial. Let's see some examples. So we saw that actually we saw the second example, but x squared minus 2 is the minimal polynomial of the square root of 2. Again, you can show it because if any smaller degree polynomial will have to be a degree 1 polynomial, which would imply that the coefficient would be a square root of 2. And we just saw before, Hippasus showed that the square root of 2 is irrational. So there is no lower degree polynomial than 2 that has a square root of 2 as a root. So x squared minus 2 is the minimal polynomial of the square root of 2. Similarly, we just claimed that, or I asked you to prove that x to the third minus 2 is the minimal polynomial of the third root of 2. There is no lower degree polynomial which has this as a root. And you can very similarly, you can also prove that x to the fourth minus 2 is also the minimal polynomial of the fourth root of 2. Okay, so these are 3 minimal polynomials for these particular 3 roots. Now let's look at the curious fact. If you take this root here, the x squared minus 2 is a minimal polynomial of the square root of 2. If you try to adjoin or to extend the rationals with the square root of 2, we saw that you get this particular vector space, a plus b times square root of 2. The dimension of this vector space is 2. There are 2 elements here. Okay, so the minimal polynomial has degree 2, and the vector space has degree 2 because it has 2 elements. The same goes for 3 and 4. The x to the third minus 2 is obviously a polynomial of degree 3. And the vector space that spans the field extension, if you add the third root of 2 to the rationals, and you want to create a field, you must also add the square root of the third root of 2 squared because of closure. Right? If the third root of 2 is there, then the third root of 2 squared must also be in the field, and it is linearly independent of the other elements, so it must be also in part of the vector space, and you end up with a vector space of 3 elements. So the degree of the polynomial is 3, and the degree of the vector space is 3. And the same goes for 4. If you add the fourth root of 2 to the rationals and try to create a field out of it, you see that you have to have a vector space of all these 4 elements. You have to okay. So the degree of the vector space is 4, which is exactly the degree of the minimal polynomial, and obviously this is a law. The degree of the vector space of the extension field is always the degree of the minimal polynomial of the root that you added to it. And here's the proof. I will not go over it. It's here if you want to take a look. It's not very difficult, but this is the rule. So the degree of a field extension of the rationals Q adjoined R is always the degree of the minimal polynomial of this root R over Q. If one exists, because we saw that some values like pi don't have any polynomial. Okay, but if one exists, then the degree of the field extension is exactly the degree of the minimal polynomial. So let's look again at the Taylor law that we saw before. If you remember, we said that if you want to start from A and extend it to B, try to find an intermediate field F, and we said that the degree of these 2 field extensions, if you multiply them together, you get the degree of the final extension. And by degree, we said that it means the size of the vector space. But now we have a different definition of degree, because we just discovered that the degree of a field extension is the degree of the minimal polynomial. You can just say restate the Taylor law in terms of degrees of polynomials. So you can say that let's see it here. So this term here, the right term, is the degree of the minimal polynomial of I over Q. The minimal polynomial is x squared plus 1, and its degree is 2. As for the second term, this is the degree of the minimal polynomial of square root 2 in this case, so square root of 2 over Qi. Now you take coefficients from Qi. This is the minimal polynomial, it's x squared minus 2. Its degree is also 2. So by the Tower law, we learned that the degree of the final field extension, Q adjoint I and square root of 2, with coefficients from Q, must be 4. Let's see some examples of this new phrasing of the Tower law. Excuse me. So if you take Q adjoint I and the square root of 2 using just coefficients from Q, we just saw now that this has to equal 4, because the minimal coefficient, minimal polynomial of I is 2, or it has to be 2. It's square plus 1. The minimal polynomial of square root of 2 is also 2. So the degree of the whole extension must be 4. Let's take a look at the second example. So now we want to add two elements, square root of 2 and fifth root of 3. So the first root that we add has a minimal polynomial of degree 2. And the second element that we add has a minimal polynomial of degree 5. X to the 5 equals 3, plus 3 equals 0, or minus 3 equals 0. Okay, so anyway, the minimal polynomial here is 2, the minimum polynomial here is 5, and the product of the degrees is 10. So this means that the degree of this extension must be 10. In other words, the vector space that spans this field extension, if you only use coefficients from Q, will be 10. Final example. Let's say I want a very high tower. I want to add 4 elements to the rationals: square root of 2, square root of 5, square root of 7, square root of 3, 33. Each of these roots are obviously a root of a second degree or quadratic polynomial. So the minimal polynomials of each of these roots is 2. I add 4 of them, so the final degree of the field extension is 16. Okay, and this will be useful for us when back to our proof, because that's if you remember, we saw this before. Powers of 2. This is okay. This is just using the Tower law. But if you look at the vector space, you can also see that the size of the vector space is 16. You actually need all combinations of these 4 square roots because of closure. So you have all the square roots themselves. You have the square root of 2 times square root of 5, and so on. You get 16 combinations of these, and all these must be in the vector space. So you have a vector space of size 16. So I have 2 proofs here that the size of this dimension is 16. One was very simple. I just used the product of the minimal polynomial degrees. But if you take a look, you see that the vector space is indeed 16, or size 16. Okay, so let's recap again. So we started with fields. We saw these fields that had to be just collections of numbers, like the rationals. They had to be close to operations like products and sums. And they had these nice properties. We saw field extensions. If you had an equation that didn't have a solution, you can also always add the solution to a field and take care to bring along all the values that are needed due to closure. For example, Qi. Then we define the degree of a field extension to be the degree of the vector space that spans it. So if we take, for example, the rationals and add the 4th root of 2, we end up with this vector space, which has 4 elements. So the degree of the field extension is 4. And we saw an alternative definition of the field extension, which might be simpler to compute, which is if you extend the rationals with the root R, the degree of the field extension is the degree of the minimal polynomial of R. So if in our case, we wanted to extend the rationals with the 4th root of 2, the minimal polynomial of this was x to the 4th minus 2. This has degree 4. So the degree of this field extension is 4. And we had this Tower law that implied that if you add many roots to the rationals, one after the other, it doesn't really, the order doesn't really matter. But anyway, if you add several roots, then the resulting field extension with all these roots has a degree which is a product of the degrees of the minimal polynomials of all these roots. And this is actually all we need for the proof. So we're done with geometry, with algebra. We're basically just going to use this final term. So let's just make sure we understand it. So we start with the rationals. And we want to add to the rationals a collection of roots. And these roots are roots to some equations of particular degrees. And the final degree of the field extension must be the product of the degrees of these polynomials, of which these roots are roots. Okay, so I just have to find the polynomial for each of these roots, take their degree and multiply the degrees. And it was important for us that it's not just any polynomial, it has to be the minimal polynomial, because you can always take a polynomial and multiply it with other polynomials with other values and still have the same root as a root. So it's important to take the minimal polynomial of these roots and take the degree from there. So we're done with algebra. In the next part of the talk, we'll use all this algebra and do some geometry and prove the impossibility of squaring the circle.